Alright, so coming back, this is part 2 of our derivative notes where we're going to be looking at kind of an idea of what is the applications that we can look at with this tangent line problem. So the tangent line problem was Leibniz. Leibniz was this idea of looking at it with this limiting perspective. But what Newton was trying to look at was this idea of instantaneous velocity. So the idea that the slope of the tangent line actually is the instantaneous velocity at that point x, and the idea is that the rate of change of a position is going to be velocity, your change in position over change in time. So delta position over change in time. And the idea is that you could look at your average velocity by looking at over a certain time interval, or we could do an instantaneous velocity, which is this idea where we use the limiting process on the average velocity to find the instantaneous rate of change. And then we can go one step farther, because then we can look at the rate of change of velocity, okay, the change in velocity over the change in time, and that's going to give us an acceleration. The same idea that how fast you're speeding up or slowing down is going to be your rate of change in velocity, which is acceleration. So we can basically talk about a position function, which is going to give, it could be a height function, gives you the height at a certain time, could be a position where it says how far left or right you are from your initial spot. But there are different applications that we can basically look at with this idea of a position function. Then we'll look at our velocity function. And just a little bit of a reminder, our velocity function is going to be the derivative, s prime of t, of your position function. That your velocity, instantaneous velocity, can be found by looking at the derivative of the position function. And then we have our acceleration function, and our acceleration function is the rate of change in velocity, so it's the derivative of the velocity. But oh no, what did I do here? How did I relate it back to the position function? It's actually what we call the second derivative. So the idea is you don't have to stop with one rate of change. You can keep going and find the rate of change, which is a second derivative. Our notation for that, instead of doing a single prime right there, we'll put little double prime, like quotation marks. But we call this the second derivative, and we read it as s double prime of t, which basically means we have to find a derivative to get the velocity, and then you have to find the derivative of the velocity to get the acceleration. So you have to basically do twice the work. All right, so let's take a look at this. In example 5, we are asking that we have a ball being thrown into the air, and its height in feet above ground at t seconds is given by this formula over here. This is a classic physics problem where you're throwing balls up and down. And this is going to be basically your position function. It's going to tell you where the ball is at any given time, how far above ground it's going to be. Now, the first thing that they're asking is, during the first second, what's the ball's average velocity? So the first thing is, when we're taking a look at this, to realize that if we're doing average velocity, that is really your slope of the secant line. And you're like, well, between what 2 points? Well, when you look at your average velocity, notice it's saying the average velocity during the first second. So the average velocity that we're looking at is on the interval of 0 to 1, because it's on the first second, or during the first second. So now once we have this idea, then we can kind of just go back and pick up from our previous page where we talked about all the different, all of the different things that we're going to do. I need to calculate the slope of the secant line. I need 2 points. Well, how do I find 2 points? I take each x value in my endpoint, I plug them into the function to get the y values, and then calculate my average rate of change. So, find where I am here. So what I basically am going to do is find 2 points, because I know that this is the slope of the secant line between the 2 points, between the x value or t value of 0, and I need to calculate h of 0, and between the point 1, h of 1. So in terms of our formula that we're going to write here, we would do h of 1 minus h of 0 all over 1 minus 0. Basically plug your stuff in, figure out what you have. H of 1 is actually 12. H of 0 is 8 over 1, which gives me 4. Now, at this point, once we start hitting application problems in AP, units are going to be very important. You pretty much aren't going to get credit for an answer unless you give the unit of measure that this is in, because it's an application problem. Now, let's think about it. We're doing average velocity. You're looking at it's a change in, kind of help us figure out our units, it's a change in height over a change in time. So if I'm looking at what units are being used for this, my height was feet above ground. So there's my feet. And my change in time, my time is being measured in seconds. So we see that we have an average velocity. Our units are feet per second. So we always want to add that in. And they really will not give you credit. If they have 1 point for answer with units, and you don't put the units, even if you have the 4, you don't get that point. So you do want to make sure that anytime you hit an application problem, just automatically fill in your units. The second thing they're going to ask you to do is to interpret what this means. Kind of give a sentence about what is this actual average velocity saying. What we have basically found, okay, and there's some key things that they're going to be looking for. They want to know that you're on an interval. They want to know that this is an average velocity. That's going to be important to talk about. And they also want to know, based on what this average velocity was, what can you say is happening over the interval to the actual height that you were looking at? If your velocity is a positive 4 feet per second, what must the height have been doing over the interval during the first second? Did it increase or decrease? You go, well, because it had a positive slope secant line, on average, over the first second, it's going to be increasing. So our interpretation, what they're going to expect you to put down, if they say, find the average velocity and interpret, you're basically going to say something along the lines of the height, which is what we're looking at, the height has increased on average by 4 feet per second during the first second. So the key things that then, now of course you know English, you can write your sentence in English several different ways, but what they're looking for is that you know that it's the height that has increased because of the positive velocity. They want to make sure that you have said the word on average somewhere in there, and you need to have the amount with the unit, and then during what interval you're looking at. So they're all parts of the things that they're going to be looking for this interpretation. Right? Now, the second part of this says, what about at t equal to 1 second, what's the ball's height? Now notice, I actually have not done calculus yet. This is all pre-calculus, finding a slope, changing y over changing x. And interpreting it, that's just English and understanding what a word problem is. So when I come down here to B, okay, B is, I want to find the ball's height at t equal to 1. Now you're also going to get into the habit of labeling on the AP. What is it you're actually finding? Well, how do I find the height at t equal to 1? Where am I plugging 1 into? That's nothing more than calculating h of 1. So you label it, you say, how am I finding it? You don't need to show any of the work in between. You're just basically going to go plug it in and plug and chug at this point. And once you plug it in, you say, well, what was the height? Well, I already did it up here. H of 1 was 12, so it equals 12. And then you don't forget, because you're not done yet, you need to figure out what your units are. This is your height. This is 12, so it would be 12 feet. Okay? So that was the easy one. And we also are going to say, well, interpret that. What does that mean? What does that answer mean in this problem? So if I go to interpret it, I'm basically going to say the ball, which is what we were looking at, is 12 feet above ground, because that's the definition of how we were defining our position function. The ball is 12 feet above ground at a time of 1 second. Okay? You want to get this idea that it's at, because this is at that instant, at 1 second. So they want to make sure that you're saying that part of it. All right, now we'll come down here to C. C is, we want to find the velocity at 1 second. Okay, so let's come down here and label it. Velocity at time equal to 1. Okay, so what is the velocity at time equal to 1? How do I find velocity, which is v of 1? I don't have a velocity function. Oh, wait a minute. What I'm going to need to find velocity, you'll remember, is the derivative of the position function, which in our problem, I'm not going to use s, even though that's kind of your generic thing. Use the letter that they give you. The position function was your height. So I need to find h prime, and I'm going to find it for t equal to 1. Now, I'm also going to, it's one of those things about the AP is kind of reading ahead. I also know that part D is finding acceleration, which is a second derivative. I am not going to use the modified form of the derivative here and calculate h prime of 1 only, simply because I'm going to need to take the second derivative. In order to take the second derivative, I have to have a formula for the first derivative. So I'm going to use just the limit definition of a derivative, and I want to find the limit as h goes to 0. Remember, this h and this h, two different things. This is the function name. This is the delta x, the change in x that we're looking at, of our h of, and you'll just kind of write it for this and we'll fix it in the next step, t plus h. This h and this h are two different. Maybe if we want to add a little curly something or another so that we know those are different here in the beginning, minus your function h of t, all over that change in x. There are times, if you look in your textbook, that they will call this delta x, and delta x, or in this problem, they might call it delta t when they look at it. But typically the AP will always pretty much use h as our change in whatever variable we're looking at. All right, so I'm just going to leave it there. It'll drop out in a second, and we won't have to worry about this h function name, h, hey, the delta x part. This will turn into the limit as h goes to 0. We plug t plus h into the function. Okay, so we'll remember that our function was minus 6t, t plus h squared plus 20 times t plus h plus 8. Then we subtract our function. Minus negative 16 is actually going to become a plus 16. I like to distribute my negative as I go. So plus 16t squared. And then you had plus 20t, but I'm subtracting, so minus 20t. And then I had plus 8, but I'm subtracting, so I do minus 8. And that's all over h. So see, now I don't have to worry about the h and the h from the function name. Then you're going to basically just do your algebra for this. We'll just do it together. So we would have negative 16t squared minus 32th minus 16h squared plus 20t plus 20h plus 8 plus 16t squared, bring everything else down, minus 8 all over h. We've done this correctly. We look for things that cancel. 16t squared will go. You have a plus 20 and a minus 20, a minus 8. Oops, go back down here. A minus 8 and a plus 8. Everything that's left has an h in it, so I'm going to factor that out. Limit as h goes to 0 of h, negative 32t minus 16h, and then plus 20 all over h. I remove the discontinuity, cancel the factor out. Now I can take the limit by direct substitution, plug in your 0, this is going to go to 0, and you're left with negative 32t plus 20. And see, I can, every time I look at this, I see a mistake that I make. That's not h prime of x, that's h prime of t. Always check yourself, make sure you have the correct variables in there. So h prime of t is negative 32t plus 20. Now, remember, what we're trying to find in this part C is what the velocity at 1 is. and v of 1 is h prime of 1. So in this problem, we're basically going to do negative 32 times 1 plus 20, which is going to give me my negative 12. And again, we're not done. We're finding an application problem. What are the units? Well, this is still a velocity, which is change in your position or change in your height over your change in time. The fact that it's instantaneous does not affect me at all in terms of the units. It's still going to be in units of feet per second. All right, and then once we get to this, we're going to say, well, what's our interpretation? Let's interpret this value that we have found. Now, let's go back to the beginning one that we did. When we interpreted the average, we did talk about the height, whether it increased or decreased. You're still going to do that, but it's not going to increase or decrease on average anymore. It's going to be at that instant how fast it is going, okay? So what we want to make sure we get in when we do this interpretation is that we want to know, first off, again, we're talking about the height. The height is, and then look at negative 12 feet per second, so it is decreasing at an, and this is kind of overkill, but I like to overkill just to make sure, instantaneous velocity of 12 feet per second. Notice I don't put the negative in because I already took care of that. It's decreasing at an instantaneous velocity of 12 feet per second at t equal to 1 second. You do have to make sure you say where you're at, because it's only at this instant that has that velocity of negative 12 feet per second. Okay? So you have to say what the height is doing, increasing or decreasing. You want to get in the word instantaneous in there somewhere, because it's not an average anymore, it's instantaneous. Give the value with units and make sure you say at t equal to 1 second. And that would be a good interpretation for that. All right, and then let's take a look at our part D, which is we want to find the acceleration. All right, so we go, I want the acceleration at t equal to 1. So, all right, well, that's plug in 1 into the acceleration function. I go, well, I don't have the acceleration function. How do I find the acceleration function? Oh, well, that's v prime of 1. That's the derivative of the velocity function, which is the second derivative of the position function, which in this problem is h double prime of 1. Now in this one, I'm going to do the shortcut because I don't need to actually find a formula for this. It's actually going to be fairly straightforward, but I can actually just go right to the h double prime of 1, which is going to be v prime of 1, and I'm simply going to do the limit as h goes to 0 on the velocity function. So it would end up being v of 1 plus h minus v of 1 all over h. Now you might want to remind yourself I didn't label it up here, but maybe I should label this as this is v of t, which is also known as the derivative. So here's my formula up here. So I'm going to do the limit as h goes to 0 of my negative 32, 1 plus h, plus 20, minus my velocity at 1. Well, my velocity at 1 we already found was negative 12, so it ends up being plus 12, all over h. Limit as h goes to 0, we end up with negative 32 plus 20 plus 12, which is going to go away. You basically end up with negative 32h over h. That's going to cancel, and constant, limit of a constant is the constant. All right, let's talk about units. This is the change in velocity over change in time. Okay, so my velocity, the units of velocity were feet per second. My change in time is going to be in seconds. So I have feet per second, which is really nothing more than feet per second squared. So that gives me my units in that. And our last thing that we're going to do for this problem is we need to interpret it, just like we did all the ones above. Okay, so our interpretation. Now, when you look at this, I mean, you got to remember this is at an instant, so we're still doing the same thing. We want to get the instantaneous part in, but this is the acceleration. So the acceleration is going to tell us some information about the velocity, what was happening at the velocity at that time. So we start writing our interpretation. We would start out by saying the velocity is, now notice this was a negative acceleration. What's happening to the velocity if you have a negative acceleration? That means that you are slowing down. So the velocity is decreasing or slowing down at an instantaneous rate. Notice I'm not saying instantaneous acceleration because the acceleration is the rate of change in velocity. So at an instantaneous rate of 32 feet per second squared at t equal to 1. All right, now the other thing is that when you're thinking about this as what was happening at t equal to 1, look at all the things that we know now. We know that the height of the ball at t equal to 1 is 12 feet, that its speed that it was traveling at t equal to 1 was negative 12 feet per second. That's how fast it was going. Well, the negative part, usually when you say height and it's decreasing, well, that must mean, hey, it's going down. Okay? The height is going down. The ball is dropping at 12 feet per second right at that instant. And the actual speed that it's dropping is this 32 feet per second squared, which should make sense to you if you've done any physics. This is nothing more than your acceleration due to gravity right there. Negative 32 feet per second squared. Everything on Earth goes at negative 32 feet per second squared. All right, so that's a nice example of a position, velocity, acceleration problem, and you're pretty much guaranteed that somewhere in the free response you're going to get one of these types of problems. Whether it's a ball being thrown in the air, whether it is a point on a line moving left or right, there's going to be some kind of a position, velocity, acceleration problem. So this is your introduction to that.